Chapter 12, Liquids, Solids, and Intermolecular Forces. Have you ever wondered why can we taste food? Every day. Why do some things taste sweet and some things taste bitter and some things taste just flat out nasty, right? Personally, I think coffee tastes nasty, but that's just my own opinion. The the sensations that we get arise from the interactions between molecules in the food and molecules on our tongues. And we have special receptor cells, and when certain chemicals touch them, they recognize those molecules and they send a signal to our brain. And you've probably been taught that your tongue has different areas, and there's some places on your tongue that taste sweet better and salty and bitter and sour. And it has to do with the molecules, certain molecules in the foods reacting with specialized cells on your tongue. And so we're going to look at those types of interactions, the interactions between molecules. They're called intermolecular forces. Inter meaning between molecules. These are not intramolecular forces, where it's a force within a molecule. These are forces between two different molecules. These intermolecular forces are unbelievably important. They're essential for most of the physiological processes that go on in your body. There are some very specific intermolecular forces. There are also less specific intermolecular forces that exist between all molecules and atoms. And the very fact that we have liquids and solids at all tells us that there are forces between the molecules. When we talked about ideal gases, one of the things we said we were assuming is that there was no interaction between the gas particles. And under a certain range of conditions, that's true. The gas particles are just operating completely independently. But when you compress them and cool them down, when you slow them down and force them into crowded conditions where they're in contact with each other more often, we do see forces of attraction between the molecules. And so the fact that the table, the bench, the floor is solid is a testament to the existence of intermolecular forces. Whether something is a liquid, a gas, or a solid at room temperature is going to depend on how strong those intermolecular forces are. There are forces between all molecules and atoms. But if the forces are very weak, then that substance is likely to be a gas at room temperature. If the forces are very strong, it will be a solid at room temperature, and then liquids are going to be somewhere in between. We've talked about this before, that all atoms are in constant motion. Even substances that appear to be still, like the bench or the floor. The particles in those substances are actually moving, they're vibrating. When I talked to you about the three states of matter and how that corresponds to students in the classroom, and how right now you guys are in the solid state. You're sitting in your chairs, and yet you are not completely still, are you? People are moving, as we should be. We should at the very least breathe and hopefully blink, because that would mean that you're not asleep. So all the atoms are moving, and the kinetic energy is also related to the thermal energy. So it's increases with heat, with the temperature. Increasing temperature increases the movement of the particles, and we call that thermal energy. So substances with weak intermolecular forces, relative to the thermal energy, are more likely to be gases. Because what happens when you take, let's see, what would be a good analogy? I'm thinking Nerf darts, those Velcro Nerf darts, right? And they stick to things like the special Nerf vest that you're supposed to have that my kids wish they had, but they don't have. But the vest is the other kind of Velcro, the loop kind, and the hook sticks to it, right? So think of something Velcroed together. How do you get them apart? You pull them, you get them to move fast enough, and they will break apart, right? And sometimes the Velcro is really strong, you have to pull really hard. And other times maybe the loops, the hooks are kind of stretched out because it's old, and it pulls apart quite easily. That's the strength of the intermolecular force. The intermolecular attraction is like the strength of that Velcro. Something that has a very weak attraction is easy to pull apart. The force that you're exerting has to do with the thermal energy, the temperature, the movement. If you're moving them fast and vigorously, that's a higher temperature, and just pulling gently would be a colder temperature. Think about something wiggling, two objects wiggling, and as they wiggle more, they're more likely to break apart, right? That's how I envision molecules. As you heat them up, take an ice cube and you warm it up, and the water molecules are vibrating more and more and more, and eventually they get to the point where they can break loose from their intermolecular attractions and start sliding around, and that's when they become a liquid. So something that is a gas, something that's a gas at room temperature is going to have weak intermolecular forces relative to its current thermal energy. If those intermolecular forces are strong, then it will likely be solid or liquid. You can think of intermolecular forces as stick-togetherness. How sticky are those particles? If they're very, very sticky, then it's going to be hard to separate them. You're going to need a higher temperature. In gases, this is not very significant because the particles are separated by large distances, and so they don't even have a chance to interact. But in liquids and solids, we could say the molecules or the atoms are touchingly close. They're touching each other. They're in close contact, and so those intermolecular forces are going to be more significant. The difference between solids and liquids is the freedom of movement. They're both touchingly close, but are they able to slide around relative to each other, or are they fixed in position? So in liquids, the atoms or molecules are in very close contact, but they're still free to move around. They can slide next to each other. That's like in lab where we get up and we move around, and we're still close and we're still interacting with each other, but we can move around. In a solid state, the atoms are fixed in their positions. They're still moving, but they're only able to vibrate. And they're always in the same position relative to each other. Pictures. Here's the gas. Particles are widely separated. And these forces of attraction depend on the distance between the particles. And when you have a distance like this, there's essentially no interaction. So gas molecules and atoms do have forces of attraction, but under normal conditions, they are so far apart from each other that they're insignificant. Liquids are much closer, and so those interactions become significant. And in a solid, they're actually fixed in rigid positions. They're just vibrating. They're just wiggling, fidgeting in their seats. So gases, and some of this is review. Gases have low densities because of all that empty space. Remember, density is mass divided by volume. So the same mass is going to take up a much larger volume, and it's going to have a small density. So gases have low densities. They have indefinite shape. They take on whatever shape their container is, because those particles are free to move completely independently of each other. They have indefinite volume. So if you make the container bigger, the gas expands. If you make the container smaller, it compresses. So they're very easy to compress because there's so much space. You can just squeeze them together, not a big deal. Their intermolecular forces are weak relative to the thermal energy. So an example is carbon dioxide. For liquids, they're going to have much higher densities compared to gases because there's essentially no empty space between the particles. So you get rid of that space, you decrease the volume, and the density goes way up. They have indefinite shape as well. You take water and pour it from a tall, I'll draw pictures. if you take a tall, skinny glass of water and you pour it into a shallow dish, the water changes shape, doesn't it? You could pour it into a round container or a square container. You could suck it up through a funny bendy straw, and it just takes on the shape of the container. So indefinite shape, but they do have definite volume. Liquids are not easily compressed. Some of them are a little bit compressible, but compared to gases, basically not at all. And their intermolecular forces have moderate strength relative to the thermal energy. Remember, thermal energy is the motion of the particles to wanting to move away from each other, and the intermolecular forces are the forces that are holding them together. This new analogy popped into my head. We'll see where it goes. So, children sitting in a classroom. Some kids are naturally more active than other children, right? Some will just sit and color for hours if you let them, right? I don't have any of those. And other kids, they just need to move, right? And so if you have a child with high energy, it's going to take a lot more discipline to get them to sit still in a chair at school without getting up to sharpen their pencil, and to get a Kleenex to blow their nose, and I need to go to the bathroom, and I need to drink a drink of water, right? Just any excuse to get up and move. So where am I going with that? It's the relative strength of the forces of attraction, the discipline of that child to sit in the chair, and that natural energy that they have. So the energy is related to the temperature. Higher temperature, more likely to get up and move around, to melt, to become a liquid, or eventually a gas. If the forces are strong, if there's a great deal of discipline holding those children together, and perhaps these are more passive children, they're just not so high energy, they're going to sit in their chairs. They'll be breathing and stuff. They'll be wiggling a little bit, but they're not going to get up and run around the room. Does that make any sense? I don't know. Was that analogy worth doing again or not? Should I do that for the Visalia people? Yeah. It's a little iffy, isn't it? Yeah, I'll have to work on that one. I think the Velcro's better. Solids. Solids have high densities compared to gases. The densities of solids and liquids are usually pretty close. There's not a huge variation. Solids have definite shape. They do not assume the shape of their container. When water is in the solid state, you take it out of the ice cube tray and you put it on a plate. The shape doesn't change as long as it's a solid. Its volume doesn't change either. So they have definite shape, definite volume. They can be crystalline or amorphous. Some of them the particles are well ordered, and others are disordered. So you can have your children sitting in neat rows in a classroom, or they could all be sitting on a rug and just kind of scattered about, disordered. Their intermolecular forces are strong relative to thermal energy. An example is sugar. Sugar is a solid at room temperature. That tells us that the forces of attraction between the sugar molecules are relatively high. The expression beating a dead horse comes to my mind. There's just way too many slides about this. Okay, so there's a liquid. They can slide around. They can take on the shape of their container. Solids have a definite shape because these are so attracted to each other they can't slide around anymore.